Hi everyone, my name is Benedikt Geiger. I'm a PhD student at the Communications Engineering Lab at Karlsruhe Institute of Technology. And I'll present today our paper Integrated Long-Range Sensing and Communications in Multi-Target Scenarios using CP-OFDM. The paper has been accepted at the SCC, so Conference on Systems, Coding and Communications, which is taking place in Karlsruhe in March 25. And this work is a joint work with Nokia Bell Labs, so with Silvio Mandelli, Markus Henninger, and my colleagues Danielle, Charlotte, and my supervisor Laurent Schmalen here at Cell at KIT. Okay, so let's dive right in. So integrated sensing and communications is expected to enable radar-like sensing in 6G by using the communication signal also for sensing. These 6G ISAC systems are expected to be based on orthogonal frequency emission multiplexing, so OFDM, due to its high spectral efficiency and low complexity for communications, but also for sensing. A crucial part in OFDM is the cyclic prefix, which should be longer than the delay spread of the channel and is prepended to each OFDM symbol. So in theory, the delay spread of a channel is arbitrarily long. However, for communications, we limit the duration of the cyclic prefix to the relevant, so to the strong taps, and ignore the belated and weak reflections since they are irrelevant for the communications performance. So these weak and belated reflections are caused by distant targets. And when we are moving now from communications only to integrated sensing and communications, we are also interested in detecting these distant targets. And so, since for an ISAC system, as mentioned, we're using the communication signal also for sensing, we will explore in this talk how we can detect these distant targets reliably by using our standard communications OFDM signal. So therefore, we consider a monostatic OFDM ISAC system where our ISAC transmitter follows a conventional communications transmitter. So we have OFDM symbols in the frequency domain, to which we apply an IFFT at the cyclic prefix and serialize the signal. The generated signal is then transmitted over a communications channel and a sensing channel. In this presentation, we will focus on the sensing part, since we are interested in how can we leverage the communication signal to detect distant targets. The received sensing signal is then a superposition of age, attenuated, delayed, and frequency shifted versions of the transmit signal. At the sensing receiver, the received sensing signal is quantized, parallelized, the cyclic prefix is removed and transformed into the frequency domain. In the frequency domain, we then estimate the channel by a point-wise division, and finally we estimate the range Doppler matrix periodogram based, meaning that we apply an IFFT along the subcarriers and an FFT along the OFDM symbols. And then in this range Doppler matrix, we get peaks at the position and the velocity of the targets which we have in our sensing channel. So here we show only a cut of the range Doppler matrix, so show only the distance for simplicity. Then in order to evaluate the sensing performance, we use the image as INR. And so the image as INR, so signal to interference and noise ratio of a target of interest, basically how much is the peak of our target of interest standing out of the noise and interference floor. And this is then a very good proxy for the detection probability, but also for the estimation performance of our sensing system. For our simulations, we consider a 5G R1 system where only a limited number of subcarriers a limited number of OFDM symbols are used for sensing. Okay, so now that we have established the system model, we have to understand how does a distant target, so you have reflection stemming from a distant target, impact the received signal. Therefore, we consider 3 OFDM symbols, all with their cyclic prefix. And if we now get here a reflection from this distant target, we can observe that the received signal is a significantly delayed version of the transmit signal. And so if the delay of our target of interest here exceeds the duration of the cyclic prefix, we can observe that the previous, so the m-1th transmit symbol ends up in the mth receive symbol. And this leads then to inter-symbol interference. And therefore the range corresponding to the duration of the cyclic prefix is often denoted as ISI-free range. However, we can also observe that in the mth receive symbol, the mth transmit symbol is not fully contained anymore. And this has 2 consequences. First, we end up with intercarrier interference and we get a reduced target peak power. To evaluate how this impacts the detection performance, we carried out a simulation where we want to detect a target of interest, for example, a drone. And so we sweep the distance of our target of interest over the full unambiguous range. And for our simulations, we assume that an image SINR of at least 17 dB is required for a successful and reliable detection. So then we can observe, if we use this conventional radar processing, which we introduced in our system model, we can observe that generally we are able to detect here a target of interest reliably beyond the ISI-free range. However, if we look at very long distances, we can observe that the image SINR of our target of interest falls below those 17 dB, resulting in missed detections at long distances. So therefore, coherent compensation has been proposed in the literature. And this coherent compensation is based on the observation that part or the part of the mth transmit symbol, which is here missing in the mth receive symbol, and up in the mth plus 1 receive symbol. And therefore, the idea here is to add this missing part to the mth receive symbol. So with this, we are able to restore the peak power of our distant target of interest. However, so in order to carry out this coherent compensation, we need to know how many samples we have to add here. And if we want to know the number of samples, or we also need to know the delay. However, usually we want to detect the target, and so the delay is not known beforehand, and this results then in a chicken and egg problem for this coherent compensation, which was proposed in the literature. And therefore, the first thing which we did is we generalized this coherent compensation. So what we propose is that you just add here a full symbol to the mth receive symbol. With this, we are able to restore the peak power of target of interest independent of its distance. If we now take another look at the similar or the same simulation setup, we can observe that with this coherent compensation, we are now able to detect our target of interest reliably over the full unambiguous range. So here the green curve is always above 17 dB. However, so far we have only considered single target scenarios. So we had just a single target of interest in our simulations. But this assumption is not really practical. So in practice, you have multi-target scenarios. And therefore, we also moved on to multi-target simulations, where we added here building, so a second target to our simulations here at 510 meters. And we observed with this simulation setup, we are still able to detect our target of interest here at 900 meters. However, if we now have buildings which are closer to the base station, we can observe that this noise and interference floor rises until eventually we are no longer able to detect this target of interest here at 900 meters. And so we can observe that with this coherent compensation, close targets result in an increased noise and interference floor. And therefore, we now have to understand how do these close targets impact the received signal if we apply the coherent compensation. And so what you can see here again is the scenario or the signal model with which we are quite familiar with from this scenario where we had only one target of interest. But now we add a second target, so here a target which is close to the base station. And here it's important to note that this second target, which is close to the base station, leads now to a reflection which is much stronger than the reflection from the distant target, since the path loss increases with the distance. So if we now apply the coherent compensation and add here this mth plus 1 receive symbol to the mth receive symbol, we can observe that for the close and for the distant reflection, we have the full mth transmit symbol in the mth receive symbol. So we have here the full peak power. However, we can also observe that we get intersymbol interference. And we start by looking at the symbol interference, which is caused by this distant reflection. And for this distant reflection, we can observe that we get intersymbol interference here from the previous, so from the mth-1 transmit symbol, and from the consecutive, so from the mth+1 transmit symbol. So, however, since the distant target causes a very weak reflection, the intersymbol interference caused by this distant reflection is also quite low. And so this mth transmit symbol experiences a coherent processing gain, and therefore this intersymbol interference stemming from the distant reflection is quite low compared to our peak power. However, if we now look at the intersymbol interference, which is caused here by this closed target, we can observe that we now add, by carrying out the coherent compensation, at the mth+1 transmit symbol here to the mth receive symbol. And here now the power of this reflection scales with this of this closed target. And since this reflection from the closed target is very strong, the intersymbol interference, which is introduced by this closed target, is also very strong. And this eventually leads or results then into rise of the noise and interference floor, which we observed on the previous slide. Therefore, we will propose in the following novel algorithm, novel multi-target coherent compensation, with which we are able to restore the peak power of the distant target, but with only a minimal increase in the noise and interference floor. So thinking here in this signal model structure, we want to reduce here this blue block because it introduces the harmful intersymbol interference. So therefore, for our multi-target coherent compensation, we first calculate the range Doppler matrix conventionally. And so in this range Doppler matrix, this distant target we are interested in might probably only have very small peak and might not be detectable. However, we get very strong reflections from the closed target. And so this closed target is then the target which will introduce this harmful intersymbol interference if the coherent compensation is applied. And therefore, we propose to apply a threshold to the power of this range Doppler matrix in order to limit the amount of intersymbol interference which is introduced if this coherent compensation is applied. And obviously the threshold epsilon should be chosen such that if we apply the coherent compensation, this additional intersymbol interference is below the thermal noise floor of our range Doppler matrix. Okay, so in the next step, we synthesize the received signal with those attenuated peaks. So we calculate the received signal for this range Doppler matrix with those attenuated peaks. So we calculate the received signal as if we had a scenario with those attenuated peaks. And here in the signal model, you can see again the scenario where we have here this strong closed reflection and here this weak distant reflection. And if we now apply the threshold, we limit here the power of this close reflection. So this is what this thresholding actually does on a signal level basis. And if we now apply the coherent compensation, we can observe that here this blue violet block is now much weaker, and therefore we introduce significantly less intersimple interference, and but we are still able to get here the full mth transmit symbol in the mth receive symbol for the distant reflection. So we are able to restore the peak power. And therefore, in the next step, we calculate the range Doppler matrix based on this compensated signal. And now we can observe that we get here this stronger peak for our distant target of interest. And in a final step, we then restore the peak power of our close target. So we basically revert the threshold which we applied in step 2. And now we end up with a range Doppler matrix in which we are able to detect the close targets and the distant targets very nicely. So to evaluate the effectiveness of our proposed algorithm, we now carry out another set of simulations, and here we sweep again the distance of our target of interest, but now we have here a second interfering close target at 105 meters. And so we can observe that with conventional radar processing, we get a performance which is very close to the single target scenario. And this is due to the fact since with this conventional radar processing, we have still the issue of those attenuated peak powers at for very distant targets. And for the coherent compensation, we can observe here a very strong decline of the performance, and this is due to this very strong noise and rise in the noise and interference floor, which is introduced by the coherent compensation by adding this consecutive OFDM symbol, which then introduces this very strong and harmful intersymbol interference. And now with our proposed multi-target coherent compensation, we are able to detect this target of interest reliably over the full unambiguous range. So the red curve stays above the required 17 dB over the full unambiguous range, and therefore we are able to detect this target of interest reliably and efficiently, also in very complicated multi-target scenarios. Okay, so let's conclude. So in this presentation, we looked at the question, how can we detect distant targets reliably using a conventional CP-OFDM communication signal. And first we considered conventional radar processing, and here we observed that we get, so generally able to detect distances, targets exceeding the ISI-free range. However, at very long distances, the image SNR falls below 70 dB, resulting in missed detections. For the state-of-the-art coherent compensation, we observed that in those single target scenarios it works quite well and we are able to restore the peak power. However, it introduces very harmful intersymbol interference in multi-target scenarios and is therefore not very practical in realistic scenarios. And therefore we proposed our novel multi-target coherent compensation, with which we are able to detect also distant targets efficiently and reliably in challenging multi-target environments. And so if you're now interested in our work, you can find our paper on arXiv. And in this paper, we take a more mathematical approach. So in this presentation, I tried to explain the intuition behind our multi-target coherent compensation and also give you a nice introduction in long-range sensing. And in our paper, we take a more mathematical approach and we also derive expressions for the image SINR for those three algorithms. So if you're further interested, feel free to have a look at our paper. And if you should have any follow-up questions, you can contact me or my co-authors. And so, first of all, thank you for your attention. And I also want to take a second for thanking all my co-authors for their support, nice discussions, and for really helping to raise the quality of the paper and research we've done, and brilliant discussions. And so thank you for watching, and bye.